So the concept of a one-sided limit allows us to extend the definition of continuity to closed intervals. Basically, a function is continuous on a closed interval if it is continuous across the interior of that interval and exhibits one-sided continuity at the endpoints. And this is stated formally as follows. A function f is continuous on the closed interval from a to b, and now to show it's closed we use our brackets instead of parentheses. If it is continuous on the open interval, parenthesis, from a to b, and here's how we sort of take care of the endpoints. The limit as x approaches a from the right-hand side of f of x is f of a. We just plug that a right in and we get f of a. And the limit as x approaches b from the left-hand side of our function is equal to f of b. We just plug the b in for x and get f of b. The function f is continuous from the right at a, continuous from the left at b. And that's reinforced down here in the figure. The first part, it says it has to be continuous across the open interval. So, here's our closed interval, the brackets on the x-axis from a to b. And if we look at the interior of the function, there's no gaps, there's no jumps, there's no breaks. So it's nice and continuous on the inside. And then our endpoints are closed off. We have these dots to say, if we plug a in and we take it up and over to the function, that height is f of a. And as we approach b here from the left, now we're approaching b from the left, if we plug b into the function, we go over and get mapped to the y-axis at f of b. So the interior is all continuous and the endpoints are defined right there and there. That is our continuous function on a closed interval. So here in example 4, let's look at the continuity on a closed interval of this. Graphically, what is that going to be? We talked about that previously, and it's a radical with 1 minus x squared. So that is going to be half a circle. It's positive, so it is the first and second quadrants, half of the circle, and the radius is the square root of that number. So in the first part here, it says, what is the domain of the function? What numbers can we plug in here? Remember, we just want positives under a radical. So if I set 1 minus x squared greater than or equal to 0, I would have, what would that be? 1 is greater than or equal to x squared. So I would square root both sides and get plus or minus 1 would be greater than or equal to x. So x is always less than 1. It's a number between 1 and negative 1. So the domain is the closed interval. Our endpoints are closed off from 1 to negative 1 because we can plug a 1 in there. If I plug in a 1 or a negative 1 and square it, we get 1 minus 1 is 0, and you can square root 0. So our endpoints are good. At all points in the open interval from negative 1 to 1, the continuity of f follows from previous theorems, 1, 4, and 1, 5. So the limit as x approaches negative 1 from the positive side, and let's check this out on the graph as we go. So we're approaching negative 1 here from the positive side. We're approaching from the right. What number are we zeroing in on the y-axis? What's our limit? Well, right over here at 0. We can just take 0 and plug it right into the function, or we can plug negative 1 right in there. 1 minus negative 1 squared will be 1 minus 1 is 0, and that's our f of negative 1. We are continuous from the right. And the limit as we approach 1 from the left-hand side. We're approaching positive 1 from the left-hand side. We're sort of sliding down the half circle toward a height of 0. Also 0 on the y-axis. And that is also equal to f of 1. If I just plug the 1 right in, 1 minus 1 is 0. Square root of 0 is 0. So we can conclude that our function, this half circle, is continuous on that closed interval from negative 1 to 1. And again, it's real nice to see the picture that goes with it too. That really reinforces it. This next example I really like. This is a nice little science tie-in. I don't know if in chemistry or anything yet you've heard about Charles's law or absolute zero. And this next example shows how a one-sided limit can be used to determine the value of absolute zero on the Kelvin scale. So on the Kelvin scale, absolute zero is the temperature 0K. Although temperatures very close to 0K have been produced in laboratories, absolute zero has never been attained. In fact, evidence suggests that absolute zero cannot be attained. And how did scientists determine that 0K is the lower limit of the temperature of matter? What is absolute zero on the Celsius scale? Well, the determination of absolute zero stems back to the work of French physicist Jacques Charles in 1800s. He discovered that the volume of gas at a constant pressure increases linearly with the temperature of the gas. You know, if you have it at a constant pressure, if you raise the temperature, the gas expands. If you chill the gas, it will contract. So the table illustrates this relationship between volume and temperature. To generate the values in the table, 1 mole of hydrogen is held at a constant pressure of 1 atmosphere. The volume V is approximated and measured in liters. The temperature T is measured in Celsius. So here at 80 degrees, nice and warm, 29 liters. As we dropped it to 60 degrees, down to 27 liters. 40 degrees, 25 liters. We get down to 0 degrees Celsius, we're at 22 liters. 7 liters less than 80 degrees. The colder we get, the more the gas compresses. So the points represented by the table, we can graph them. And I have figure, yeah, here it is right here, figure 133. Moreover, by using the points on the table, you can determine that T and V are related by a linear equation. So they noticed, as they plotted those points, it's a very nice straight line. It follows a very linear relationship. So they came up with this formula. Volume equals that decimal times temperature plus this constant. Or if you solve for T, T is equal to V minus that number, all divided by that number. So by reasoning that the volume of gas can approach zero, but can never equal or go below zero, you can't have a negative volume of gas, you can determine that the least possible temperature is given by, we want to look at our function. The limit as that T, as our volume approaches zero from the plus side. We got a little bit less, we're on the plus side of zero. We're getting it so cold that volume is down to almost nothing. What happens as we approach a volume of nothing? So we just use direct substitution. Plug that in, we get 0 minus that number, we divide that out, and we get approximately negative 273.15. That is our temperature in Celsius of absolute zero, or 0 Kelvin. So 0 Kelvin, 0 on the Kelvin scale, is approximately negative 273.15 degrees on Celsius scale. The following table shows the temperatures in example 5 converted to Fahrenheit. You can try repeating the solution shown in the example using these temperatures and volumes, and use the results to find absolute zero in Fahrenheit. And note Charles's law for gases, assuming a constant pressure, can be stated as V equals R times T. That's Charles's law, where V is volume, R is the constant, T is the temperature. In the statement of that law, what property must the temperature scale have? Again, here I like the picture. As here on the y-axis is our volume of gas. Here we have a higher volume of gas. As the temperature drops, we're compressing the gas. It's getting smaller and smaller. We cannot compress it down to zero, so we're going to have an open-ended, part of the graph here. But we can approach zero. As we approach zero on the y-axis, we're approaching that temperature of that negative 273.15 degrees. Nice little science tie-in to our calculus. Okay, now we have some properties of continuity. In our Chapter 2, Section 3, we studied several properties of limits. Each of these properties yields a corresponding property pertaining to the continuity of a function. For instance, Theorem 1.11 follows directly from Theorem 1.2. We have our properties of continuity. And here, this is from before, we have our properties of limits. And you're going to notice these are, very, they correspond quite nicely. So, the theorem says if b is a real number and f and g are continuous functions at this point c, then the following functions are also continuous. So if we take a continuous function and we multiply it by just a number, a scalar multiple, the resulting function is continuous. Sum or difference. If we have one continuous function plus or minus another continuous function, the result is another continuous function. Or if we have two continuous functions and we multiply them together, the result is also a continuous function. And it also works for quotients. If we take those two functions and make them into a quotient, as long as, our denominator is going to not equal 0 at point C, as long as g of c does not equal 0, a continuous function divided by a continuous function is another continuous function. Again, these are very, very similar to our properties of limits. If we had a limit, we could do a scalar multiple and still be fine. We could sum two different limits together. We could do the product of two different functions' limits and the quotient. So all those properties of limits also correspond to our properties of continuous functions. So the following types of functions are continuous at every point in their domain. Any polynomial, continuous everywhere. A rational function with a non-zero denominator, continuous everywhere. Radical functions. Now remember, the key here is it says at every point in their domains. If we look at a simple square root function, here's our xy axis. Our square root function is going to look something like this. And sure, our function is not defined over here for negative x values. We can't take square roots of negatives with a real answer. But this function is continuous at every point in its domain, from 0 to the plus side. And our trigonometric functions, sine and cosine, are continuous everywhere. They're just our waves. But if you think about tangent and cotangent and secant and cosecant, there are vertical asymptotes for those four trig functions. But remember, they are continuous across their domains. Those asymptotes are numbers that are not in these upper trig functions' domains. But the functions themselves are continuous in their domains. So by combining this Theorem 1.11 with this summary, you can conclude that a wide variety of elementary functions are continuous at every point in their domain. Let's see here. F of x is x plus the sine of x. Well, x is a continuous function, plus sine is another continuous function. A continuous function plus a continuous function results in a continuous function. And again here, key phrase, at every point in its domain. Here we have 3 times the tan of x. So that is 3 times a continuous function across its domain is another continuous function. A multiple times a continuous function results in another continuous function. And let's see here, the last one, our numerator, is a continuous function, x squared plus 1. So we have a continuous function. Here we have cosine of x, which is also a continuous function. So here we do have a continuous divided by continuous. That's going to equal continuous. And you might think, okay, I know there's some times where cos of x is equal to 0. There's times where cos x crosses the x-axis. Well, here when we divide by that is going to create a vertical asymptote, and that's just going to be not part of the domain. So continuous divided by continuous is continuous. And the next theorem, which is a consequence of Theorem 1.5, allows us to determine the continuity of composite functions. So here now is not just sine of x, it's sine of 3x. 3x is continuous, sine is continuous, so the composite is continuous. Here we have under the radical x squared plus 1, and that's composed with the square root function. And so it is continuous, composed with a continuous across its domain, so that is also going to result in a continuous function. And the same here, we have our 1 over x. Of course, that's continuous across its domain. Of course, we can't plug in a 0, but that's continuous across its domain. Tangent is continuous across its domain, so that composite will also be continuous. And that's what we got here in the theorem box. If g is continuous at c and f is continuous at g of c, then the composite function given by f composed g of x is equal to f of g of x, and that is continuous at point C. So in example 7 here, we're going to test for continuity or describe the intervals on which these functions are continuous. Now the first one is just the simple tan function, the tan of x. And if we remember our pre-calc, our basic graph shapes, remember that tangent, of course, goes through the origin, and it goes up to the right, down to the left, and our first asymptote occurs at half pi, and our first one on the left-hand side would occur at negative half pi, and the period of that function is 1 pi. So if we want to describe the intervals, we could write them out in this type of notation. We would use parenthesis, negative half pi, comma half pi, close it with a parenthesis, and then our next interval would pick right up at pi over 2, comma 3/2 pi over 2, that 1 pi jump. And we use those parentheses because right through there is where we have our asymptote. We could not have brackets there. We have to have that as our parenthesis. And we could continue on in that manner. And then this one would pick up at 3/2 pi, comma 5 pi over 2, parenthesis. And again, where those parentheses are our asymptotes. And I think they do a little bit better picture there. Yeah. F is continuous on each open interval in its domain. And we're just jumping from, half pi every 1 pi after that. So I guess we could write it like this also. Pi over 2 plus or minus, some integer n times pi. Those would show us our asymptotes, and those would be the numbers not in the domain, or where our function is not, those would just be where our asymptotes lie. But remember, those functions are continuous everywhere in their domain. Aha! Now this next one is a little trickier. We have the sine of 1 over x if we're not equal to 0. And if we do have an x value of 0, our output value is 0. So here we have a little piecewise function going on. But let's think about this inner part of the composite. We have our 1 over x. 1 over x is not continuous at 0. We can't plug a 0 on there. We'd get 1 divided by 0, and we all know what happens there. But the outer of the composite, the sine of something, is continuous. Continuous for all real numbers. But therefore, we use it. I don't know if I've shown you this before. Little triangle dots means therefore in mathematics, especially mathematical proofs. We have 1 over x is not continuous at the reals, or is not continuous at 0. The sine function is continuous. Therefore, when we compose them, our composite, the sine of 1 over x, is not continuous at 0. Not continuous at 0. So even though our function is defined there, we're not going to be continuous. It's not all going to come together and make a uninterrupted graph. And let's see here. So 0 is the one point where we're not continuous. So we could probably describe this as from negative infinity to 0, parenthesis, and then 0 to positive infinity. We're just undefined there at 0. And let's check out what the graph looks of this. This is our oscillating behavior graph. If you remember sine of 1 over x when we first started about limits, we said as we approach, we're going to have infinitely many oscillations. Even if we pick the tiniest interval around 0, we will have infinitely many oscillations. Even though this function is defined at 0, we're not going to have a continuous function. Now this next one might be the hardest one to wrap your head around. If you see the difference we have here in part C, we've just put an x in front of what we had here in part B. X times the sine of 1 over x. And this is called dampening. This is dampened by a factor of x. Dampened by x. And here we can sort of use the squeeze theorem on this. We know from our pre-calc class, of course, that this number in front of the sine function, that is our amplitude, and that'll tell us how high our peaks and valley goes. So if we think about, what are the values can this function take on? Remember, sine usually goes between 1 and negative 1. When we did pre-calc, you might remember this. Sine of x goes between 1 and negative 1. Well, now, since we have this x out in front of there, let me even back that up a little farther. X times the sine of x. Actually, I got to have my 1 over x in there. x times the sine of 1 over x is going to be sandwiched in between whatever our amplitude is. And that'll be over here the absolute value of x negative and just the plain old absolute value of x. So again, that's a lot like what we did in pre-calc. Oops. Just the basic sine of x always drifted between 1 and negative 1. Now that amplitude just made this x and x, and of course we have to make that one negative on the left-hand side. So what does this mean as x approaches 0? If we start making that closer and closer to 0, these numbers are going to correspond and get closer and closer to 0. So we're going to have 0 is less than or equal to our function, x times the sine of 1 over x, which is going to be less than or equal to 0. So by that squeeze theorem, as x approaches 0, the limit as x approaches 0 of our function, h of x, they called it up here, that's just going to equal 0. And it's going to be continuous for all real numbers. So our value there is 0. Our limit as we approach it is also 0. So since we're defined at 0, and as we approach that limit, that is also equal to 0, here we're actually going to be continuous for all real numbers. Continuous for all real numbers. And I think the graph of this is pretty interesting. We just put that times x in the front, and we call that it was dampened by a factor of x. Well, what happened? Here is our y equals the absolute value of x positive, just a straight line going up at a 45-degree angle. We have our y equals the negative absolute value of x. That's our line going downhill here. And now our function is corralled in between there. So, we are going to have oscillations going on, and we're going to be bouncing back and forth between those. But as we zero in, our limit approaches 0. Our function is defined at 0, as 0. So, that is going to make that become continuous at the origin. Okay, hold on there. I think we're almost done here. Yes, the intermediate value theorem is the last thing we discuss in section 2.4. And the IVT says if function f is continuous on the closed interval from a to b, and f of a does not equal f of b, and k is any real number between f of a and f of b, then there is at least one number c in that interval from a to b, such that f of c equals k. And let's see if we can, do a little bit of graph on that to help clear it up a little bit, maybe. I'll just do a quick little, oops. Just do an XY axis here. And it says f is continuous on the closed interval from a to b. So here I have my endpoint a, here I have my endpoint b, and I know I'm continuous across the whole thing. And then it says f of a does not equal f of b. So f of a and f of b are different heights on the y-axis. I'll put my f of a up here. I guess it doesn't matter. This would be f of a, and that would be at a height right here. And then maybe f of b is a little bit lower. If I come across to the y-axis, this is f of b. So we're continuous across the closed interval from a to b. F of a does not equal f of b. They're at different heights. And we're continuous, so we can just, draw a graph in here, however you want to connect them without lifting your pencil off the paper. It says, then there exists at least one number c somewhere in here. Well, let's back up. And k is any number between f of a and f of b. So somewhere between f of a and f of b, there has to be some number in here, k. Then there exists some number c down here in the x-axis between a and b, such that f of c is going to equal k. So if I go from point k here over, I'm going to hit the graph at least once and go down and say, well, that has got to be some point c. F of c is equal to that number k. And it says at least one number. If I keep going across here, the way I've drawn this graph, it hits again, and I'll go down. There's another number c that f of c is equal to k. We'll call that c sub 1. And it even happened again, depending on how I had drawn that graph. Let me back up. Oh, I did too many dots there. if I try to draw that line without any curves to it, if I just do, a straight line going down, it might be easier to see this idea. I could pick any number between f of a and f of b. Up here, I could call this point k. From that point k, I got to hit the graph somewhere. I'm going to go down. That's point C. Or maybe I didn't pick k so high. Maybe I pick k down here. This theorem says that I have to go over, hit the graph somewhere, and there's going to be a point C somewhere between A and B. Then when I plug it into the function, I get that value k. And now let's make a note here. The intermediate value theorem, the IVT, tells you that at least one number C exists, but it does not provide a method to find that exact number. Such theorems are called existence theorems. By referring to a text on advanced calculus, you'll find a proof of this theorem that is based on the properties of real numbers called completeness. The IVT states that for a continuous function f, if x takes on all the values between a and b, f of x must take on all the values between f of a and f of b. So the IVT guarantees the existence of at least one number, C, in that closed interval from A to B. There may be, of course, more than one number C, such that f of C is going to equal that number k, as shown in figure 135. This is like the picture I drew. Here's our interval from A to B. We're going to go on the y-axis from f of A to f of B, and if you pick this value for k, you're going to look straight across and run into the graph several times. A function that is not continuous does not necessarily exhibit the intermediate value property. For example, the graph of the function shown down here in this figure on the right jumps over the horizontal line given by y equals k. And for this function, there is no value c in our interval from a to b, such that when we plug c into the function f of c, we'll get that value of k. So here, this is why we need the idea of continuity. Here's our interval from A to B. We're not continuous across the interval. We have this gap, or it could even be just a tiny little hole. But we could pick a value of k that when we look across, we don't find the function at all. So there is no value c down here that when I plug it in, I'm going to go up and get that value k. So the intermediate value theorem often can be used to locate the zeros of a function that's continuous on a closed interval. Specifically, if f is continuous on the closed interval from a to b, and f of a and f of b differ in sign, the intermediate value theorem guarantees the existence of at least one zero on the closed interval from a to b. And let's see here, now they're saying f of a and f of b differ in sign. So one of them is going to be in positive y value territory. Maybe f of b is down here in negative y value territory. So if, one of them is on each side of the x-axis, that means when we draw the function, we have to cross the x-axis somewhere. That's going to be a zero of the function. So the IVT guarantees the existence of at least one zero of the function across that closed interval. And we're going to check that out here in example 8. So it says here, use the IVT to show that the polynomial function x to the third plus 2x minus 1 has a zero somewhere in the interval from 0 to 1. So here's our function, and the easiest way to do here, I'm going to say f of x, it's continuous on the closed interval. F of x, continuous on 0 to 1. It's got to be continuous on that interval to apply the IVT. So what we're going to do now is plug in the endpoints. Plug in the endpoints. So our function was f of x is equal to x to the third plus 2x minus 1. And I'm going to first plug in the endpoint 0. So f of 0 is going to be 0 to the third plus 2 times 0 is 0 minus 1. That's equal to negative 1. So f of 0 is a negative number. Now let's plug in the other endpoint, positive 1. F of 1 is going to be 1 to the third plus 2 times 1 is 2, minus 1. So 1 plus 2 is 3, minus 1 is 2. F of 1 is equal to positive 2. So what we have here is one endpoint is negative, the other endpoint is positive. So we can conclude, let me get this picture out of the way, by the IVT, by the intermediate value theorem, there must be a C, there must be a number C in our interval from 0 to 1 such that f of c has to equal 0. And this, I think, is most easy to see graphically. Oop, what did I do there? There we go. Our interval goes from 0 to 1 on the x-axis. When we plugged in 0, we were down below the x-axis in negative y territory. When we plugged in the positive 1, the other endpoint of the interval, we were up here at positive 2. There is no way that you could connect this dot on the left and this dot on the right without crossing the x-axis. So that's what this intermediate value theorem is guaranteeing us. They're saying that somewhere in between 0 and 1 on the x-axis, we have to cross the x-axis. When we plug c into the function, we'll get an output of 0. And again, this is an existence theorem. It doesn't necessarily tell us how to exactly find that point C. It just tells us that point C does in fact exist. Alright, and that is the end of this section 2.4 on continuity and one-sided limits. In chapter 2, we only have one more section to go, 2.5. That'll be infinite limits, and then I promise we're done with chapter 2.